This is the final fourth part of the chapter 3.3, and we will talk about the linear transformations and how we can use the linear transformation to evaluate the areas in 2 and 3 dimensions. Okay, and there is a theorem 10 in the textbook which has a really useful result. If we have a parallelogram, any parallelogram which is trying to transform into using some kind of linear transformation, annual transformation will be okay. Then we can find the area of the image under the transformation by calculating the product of original area of parallelogram and the determinant of matrix of the transformation. And we can also expand this result into the 3D when we have a parallelepiped formed by the three vectors. And again, we're applying to the linear transformation to this parallelepiped. In this case, the volume of this transfer of the image under the transformation will be a determinant of the matrix of the transformation by original volume of our parallelepiped. And these results can be actually extend farther because we often can estimate the area of any image by breaking it down into the small squares. So like, for example, in computer graphics, any image on the computer screen is break down in a sets of pixels, which is just a square dot. And we are often need to transform these images. Like, for example, here there is a shear transformation, which you probably already done 3 times this morning. You drag some object on the screen, you shrink and compact them. It's all of them to preserve the area. You need to know how to calculate it. And we can extend, therefore, we can extend results of theorem 10 on pretty much any bounded object. If we have any bounded objects under the linear transformation, we can calculate the area of the image as a product of original area times the determinant of matrix of the transformation. So it is a very powerful result, and it's used computer graphics extensively, but it also can do like used to make our regular daily calculations a little bit easier. For example, let's just use these results to calculate the area of the ellipse. For example, we are given an ellipse which is bounded by the with a given minor and major axis A and B. So our A and B are positive numbers, and this is probably the formula which familiar to you. Probably see the equation for ellipse more than once in your previous courses. But this time we're not going to look at it as an ellipse. We will look at it as the linear transformation of the unit circle. So we have a disk D over there, which is just basically include the unit circle. And what we are doing, we're applying a linear transformation to stretch it and into the ellipse with main axis A and the minor axis B. So let's go ahead and try the matrix for this transformation. And we know that the easiest way to find the matrix of transformation is just basically track where the unit vectors 0, 1, and 1, 0 goes under the transformation. Let's start from the point 0, 1. Under the transformation, it goes over here in the point 0, 1, 0, A, 0. So, okay, let's look at our second unit vector, point 0, 1. This one goes into the point 0B in our ellipse. So we have 2 images of our unit vectors. To find the matrix of transformation, we just compile them in a single matrix, which happen to be pretty simple here. And the best part, we can find determinant by just multiplying the diagonal element, and it will be equal AB, the product of major and minor axis of our ellipse. Okay, so now let's just find the area. Our area is equal the area of our image under the transformation T, which is using our formula from theorem 10 will be a determinant time of the area of original circle D. And our determinant we just found, that's equal AB, and the area of the unit circle will be pi r squared, and r is equal not 1 here, so it will be just pi times AB. And if you don't trust me, you can go ahead and check in any pre-calculus book. You will find the formula for the area of ellipse, but you don't have to memorize it right now because you know the determinant and you know the linear transformations, and you can find it derive it anytime. Okay, so I'd like you now to go and practice a little bit more the properties of linear transformation and calculating the areas of 2- and 3-dimensional spaces under the transformation.